This meeting is being recorded.
So, hi everyone. Thank you for joining us today. We have Peter Anderson in house today, which is an honor, and we are very excited for him to join us in the Embodied AI lecture series. Peter is a research scientist in the language team at Google Research, and his research interests include computer vision, natural language processing, and AI. And works at the problems at the intersection of computer vision and natural language processing. More specifically, he's been focused on grounded language learning, particularly in large-scale, visually realistic 3D environments. He's won many awards, including 2 medals in finance from the University of Sydney and computer engineering from the University of New South Wales, which I found very interesting, very different backgrounds. And with that, thank you so much for joining us, Peter, today. And we are very excited to hear about your work. Take it away.
Thanks so much, Kiana, and thanks everyone for having me. I think this lecture series is such a great initiative, and yeah, really excited to be part of it. So today what I wanted to talk about is synthetic data for language-guided agents. And so when we say language-guided agents, I'm generally interested in basically trying to build robots that can follow natural language instructions. The particular way that we've been pushing in this direction is to focus on navigation. So there's a couple of examples of what that looks like here. There's sort of different flavors and data sets and simulators for this type of problem. The one on the left is using the RxR data set in the habitat simulator. So this is a sort of continuous environment and instructions which are multilingual. And so this is, if you like, the sort of most difficult setting, which still has a long way to go until we reach human performance. And actually, by the way, this challenge on the left, the leaderboard, is open for submissions as part of a CVPR challenge that will be announced at the Embodied AI workshop. So I definitely encourage anyone who's interested to have a look at that and the starter code that's available. The version on the right here is a little bit simpler data set and navigation by sort of jumping through nodes in a graph. But the sort of overarching aim here, either way, is to understand language and to be able to ground the instructions into, I guess, 2 things, visual entities in the environment, and secondly, actions. So here the actions are things like turning left and right and moving, but ultimately, actions should be much more than that and include manipulating the environment, moving things around, etc. But this is still really the same problem. So that's what I'm particularly focused on. What I want to do now, though, is take a detour away from that and talk about some other things that have been happening in, I guess, adjacent areas. So one detour is to think about this task, which is called point goal navigation. And this is a navigation task where the goal is given to the agent in sort of agent relative coordinates. So it's a somewhat artificial task in that it's sometimes, I think, at least for me, hard to think of a scenario where the agent would sort of know where they're trying to get to in some coordinate system, but not have a map. But nevertheless, there's things that we can learn from this task. And in this particular example here, you can see an agent navigating through the map and they reach this goal. And in work that Eric Wymans and collaborators have done, they can basically solve this task perfectly. But in order to do that, they need a huge amount of training experience, which basically works out to be about 2.5 billion steps or interactions with the environment. So I guess that's the sort of detour one, is that you can solve navigation problems if you can get huge amount of training experience. The second quick detour I want to take is to look at what's been happening in sort of vision and language understanding. And in this area, noisy data sets mined from the web have been continuing to redefine the state of the art for vision and language models. So there's a couple of examples listed here. There was some awesome work from OpenAI DALL-E for text-to-image generation, and also the CLIP model that really pushed what was possible for image text dual encoders. And then following that, there's been work from Google on the Align model, and more recently Mural, which is a multilingual version of these image text dual encoders that's extremely powerful. And by powerful, what these models can do that wasn't possible a few years ago is be proficient at multiple tasks, to do things in a sort of zero-shot way, and to be surprisingly compositional in terms of the vision and language understanding that's displayed. So for example, if you look at Align and look at some fine-grained queries, at the top here, you might run a query for images that look like Van Gogh's Starry Night, and then you might want to focus on the details and get the image at the top left, or in black and white, and then you'll get the image next, and so on. And so the embeddings and representations learned in these models really have a very, very fine-grained understanding. Secondly, they're sort of surprisingly compositional. So you can do this sort of arithmetic and embedding space where you take an image on the left at the top, you subtract the word embedding for cars and go and do a search, and you can get, you know, a streetscape with cars removed, or you can extract the word embedding for trees from the visual embedding of the image on the left, and now you can do retrieval and get, you know, a similar image but without trees and so on. So there's this sort of compositionality. And what underpinned all of this is, again, a huge amount of training data. So in this case, the Align model is trained on 1.8 billion noisy image text pairs mined from the web. You can see these are examples of the training data, and it's pretty noisy. There's all sorts of trash in the text, but nevertheless, the model trained on this brings sort of unprecedented performance to vision and language understanding. So that's all a very roundabout detour, but what I want to get to, I guess, is that combining massive amounts of training data with fairly generic model architectures really works. And what I've been thinking about, I guess, is what does this mean for language-guided navigation agents, or language-guided robotic agents in general? Because we clearly can't just go on the web and scrape millions or billions of robot instructions and their corresponding action sequences. So how do we sort of take advantage of this trend? The first natural idea is one that's been pursued heavily in the sort of vision and language navigation community so far. And this is to look at transfer learning. And just to give a quick example of how this can help, we took this is an unpublished, you know, small experiment, but we took a recent state-of-the-art model, which is called recurrent VLN BERT, and we just replaced the image features which previously had been trained on the Places 365 dataset. We replaced these image features with features from Mural, which is one of the models that I just mentioned, and that improves the success rate at following instructions by about 5%. So that's a really big improvement, but it's still far below the human success rate. So of course you might then say, okay, but that's just the image features, and the kind of important thing here is the combination and the interaction between the vision and language. There's plenty of work being done, I guess, in this direction as well. So with Arjun from Georgia Tech a couple of years ago, we did some work taking a pre-trained image text transformer and incorporating that into a vision and language navigation model. This pushed the success rate even further, but with the limitation that this was just actually a ranking model that would take instructions and paths as an input. And so it's a strictly easier task here because it's sort of breaking the partial observability of the environment. And again, it's still way behind human performance. And this particular data set is the room-to-room data set. It's not even the hardest data set out there. So transfer learning on its own isn't enough to kind of get the benefit of this data. And that brings me to the sort of next idea, which is really the focus of this talk. And the direction is to use synthetic data, and in particular, synthetic language data, based on the idea that there are aspects of language that our language-guided agents are just not going to be able to learn unless they learn it in an environment. And examples of that would be things like spatial relations. It seems very difficult to me to imagine how a model pre-trained on images and text from the web, or even just pre-trained on text data alone, is ever going to sort of understand the fine nuances of spatial relationships between two objects, or between objects and the observer, and so on. So that really is the motivation that guides this sort of whole research agenda. And I'll just kind of lay this out quickly, and then I'll stop for a bit of discussion. But basically what we're interested in is, on the one hand, generating environments, because even the training environments we have are probably not sufficient. Secondly, as I've hinted strongly, we're interested in generating instructions to describe action sequences in those environments, and doing this automatically. In order to do that, it also brought up the problem of how you actually evaluate whether an instruction is good or not. This is something that we dealt with previously in the work that's linked here, and I won't talk about today. And to make all of this work, you also need some good quality human annotated data to start with. And so there is a dataset collection aspect to this sort of research agenda. This is also something that we did a while back with the RxR dataset, so I won't talk about that today. But I am going to talk about the first two aspects of this, and I will stop right there for questions and discussion first.
This is actually a very important problem, I think, that you're trying to tackle here. And I think we've all thought about it a lot, because RL is just takes forever to train, basically. So what the approach of having synthetic data for language instruction, it reminds me of the whole things that we had with Clever. And how when we were generating those data set, when researchers were generating those data set, at some point they realized that it's not really something that it's even understandable for a human, and the models were kind of like overfitting. And I think you might actually like answer this question later on, but how do you make sure that these instructions are still realistic?
Yeah, great question. As an aside, we actually did build a template-based navigation instruction generator that was in a supplementary of one of the previous papers. And we found that we could train an agent on that and get very, very high success rates for that agent to follow those synthetic instructions. But that didn't help much when it came to following the natural language instructions provided by a person. And so I think what you've said is exactly right, that if we're doing this synthetic stuff, we have to match as closely as possible the sort of, I guess, or cover the domain of, you know, the huge variability in instructions that a person might actually issue. In order to do that, what we are basically doing in the evaluation is to get people to follow the instructions, and that's the primary evaluation. So we basically are focused on creating synthetic instructions that a person can follow, and we assume if people can follow it, it's going to be good for training the model. Anything else, or shall I carry on ahead? Okay. So first of all, let's jump into this part about generating instructions. And this is predominantly based on some recent work that will appear in CVPR. So the way that we formulated this task, so here we're talking about navigation instructions. And so the input to this model is going to be a sequence of 360-degree sort of panoramic images captured along some route in an indoor environment. And what we're trying to do is generate instructions that are accurate and fluent so that people can follow them. And we're going to do this in multiple languages because we have multilingual data in the RxR data set that we'll use. So in prior work, this is something that has been tackled before in some previous papers on vision and language navigation, in particular Daniel Fried's work, and then some follow-up work as well. Although it was never, I guess, the primary focus of these papers. But we did some work previously to do human evaluations on the existing instruction generators. And we found that there was still quite a way to go, I guess. So when we looked at the existing work, we found that there was a lot of hallucination in the generated instructions and that people had a very hard time following them. And the reason for that is if you look at this mapping that we're trying to learn, there's this huge amount of visual information in the environment. And then there's this very long instruction that references all this visual stuff as the output. And in order to learn, I guess, that input-output mapping without any other structure would just take a huge amount of training data, and we're sort of back in the same problem of not having the training data that we've always been in. And in particular, I guess this is more difficult than something like image captioning because there is so many more pixels on the input. And not only that, most of the stuff in the environment will never be mentioned in the navigation instruction because the instructions are very selective and they only mention certain landmarks. So in order to overcome this, what we basically proposed was a two-stage approach. First of all, we'd have a stage one to detect some salient landmarks that would be useful to refer to in a navigation instruction. And then from there, we'll have this second stage that will take those landmarks and transform that into a fluent navigation instruction. And this is all very well in theory, but it kind of just creates another problem though, because we don't have those landmark annotations that we could use to train either as the output of the landmark detector or as the input to the instruction generator. So that became the focus in this project, was to, first of all, see if we could bootstrap a data set of landmarks that would correspond to the natural language instructions in an existing data set. So the way that we did that, first of all, is that we built this on top of the room across room, or the RXR data set. So this is about 126,000 human-written indoor navigation instructions in English, Hindi, and Telugu. And in order to, first of all, identify which parts of these instructions refer to landmarks, we used a dependency parser and some simple rules to extract landmark phrases. So, for example, out of the particular instruction here, we extracted things like commode, washroom, and white cabinet as landmark phrases. And what we wanted to do next then was to ground each of these landmark phrases into the environment. And we have a kind of helpful addition, I guess, from the original RXR data set. And what that is something called a pose trace. So while the annotators were annotating navigation instructions, they actually did this by recording their voice. And while they were recording their voice, we kept a record of everything that they looked at along the way. And what that means is that we can constrain our landmark grounding problem. Even in the simplest sense, we know that the landmark that we're trying to connect to has to be something that the annotator looked at. Okay, it clearly can't be something they didn't look at, because if they didn't look at it, they wouldn't have mentioned it in the instruction. And so we have some kind of constraints there that we can use, because in fact, when annotators do this type of problem, they actually ignore about half of all the pixels in the environment anyway. So they're quite selective about how they pay attention. I'll just play this. It won't actually play the audio because, oh, maybe it will.
Turn to your left. You can see 2 wooden steps.
Is that audio coming through?
Walk forward.
Yes, yes.
By crossing a wall paint, which is to your right side. You can see an open door to your left side. Enter into it. This is a gym room. Move forward and walk till the end.
Okay, I'll stop it there, but just to give some sense of what this data looks like, the way we've sort of been able to align the text of the instruction to all of the things that the annotators were looking at. And so we'll use that to help figure out where the landmarks are that match the instruction.
And can I ask a question?
Yeah, please do.
So in the previous slide, basically when you are saying that you're rounding them, it's just the scene and not like a bounding box in the image, in the first person camera view, saying exactly what object they're looking at.
So we're going to ground it to a bounding box, like representing a perspective camera view in a particular direction at a particular location. It's not going to be perfectly aligned as well as it would be in like an object detection data set, for example, but it should be fairly close. So
But
I can show you some examples of that shortly.
did you try combining this with an off-the-shelf object detection to see if you can get any better results?
Yeah, we did. So what we actually combined it with was the image text co-embedding model, one of the ones I mentioned earlier called Mural, which is basically similar to Clip or similar to Align, but it's a multilingual version. And this model is extremely strong in terms of these groundings. So ultimately what we use is a combination of 3 types of supervision. We've got some weak supervision from the pose trace. We've got some weak supervision from the image text model to sort of tell us like which of these views align to the text fragment. And then we've used a dependency parser as well to kind of figure out which words in the instruction are actually landmarks. So it's kind of tying these 3 things together.
I see. Thank you.
So the way that we tied those 3 things together is we basically took, along the top right here, all of the images in the pose trace, which is, if you like, the sort of video recording of what the annotator looked at. And then we took all the landmark text spans down the sort of left-hand side. And for each of these, we had an alignment score, which was based on the image and text embedding from Mural. And then what we basically did on top of that is we added one more constraint, which was to use CTC decoding. And the purpose of this was to take advantage of something that we noticed, which was that the order that the annotators look at things in the environment is pretty much always the same order that they talk about them in the instruction, because they were sort of doing this sequentially as they walk through. So the CTC decoding on top of everything here adds that constraint that basically the order of the landmarks in the instruction will match the order of the landmarks in the pose trace, and that helps a little bit further. So let's have a look at how does this come together and what does it look like? Here's an example of a full instruction from the RxR data set, and then highlighted in blue and numbered is sort of each of the landmark phrases, and then those numbers aligned to the images below that indicate where that was grounded to in the environment. So like we talked about before, the sort of alignment of bounding boxes isn't perfect. For example, let's have a look at number 5 is a sync counter, and number 6 is a counter. These are not perfectly aligned, but nevertheless, the grounding is pretty strong. And I think out of all of these, the only one that's actually wrong is number 10, where it refers to a kitchen. And even though that does look more or less like a kitchen, I guess, in actual fact, that was a dining room next to the kitchen in this particular building. And I think the reason for that error is because of the CTC decoding constraint that enforces this ordering. But yeah, nevertheless, in most cases, that helps. So this is what this bootstrapped landmark data set looks like. And all in all, we constructed 1.1 million of these grounded landmarks across the 3 different languages. Another way to look at this is just kind of randomly as image text pairs. So here's a more varied example of the types of indoor visual landmarks that are represented in the data. Okay, so with the benefit of that silver landmark data, we now sort of have everything we need to train this 2-stage approach. The first stage, we use an object detector to identify landmarks in the 360-degree panoramas. For that, we use Sentinel. And in the second stage, we basically are going to map from a combination of text and landmark images through to a text output, which is the instruction. And for that, we basically use a multilingual encoder-decoder transformer based on MT5, which is a fairly, I guess, conventional transformer encoder-decoder setup. In terms of how the data is actually represented in each of these stages, so the input to the landmark detector looks something like this. We basically give it a equirectangular representation of the 360-degree view. We add some circular padding to eliminate the sort of edge discontinuity. And then we add some color coding that indicates the inbound and outbound direction of the path that the agent's actually following. And that just helps to take advantage of some priors. For example, the landmarks that people refer to are often close to the direction that you're moving to next. And so in this case, the landmark detector predicts this red bounding box. From that, we can extract a perspective view, which is basically this, which will be the input to the next stage of the model. The second stage of the model, what we basically provided as the input format is this combination of text as well as visual features representing those landmarks. And so basically what we do is construct this fairly simple template that provides a textual description of the orientation of each of these landmarks relative to the path. And secondly, it provides a kind of description of the actions that are taken in between different landmarks. So it says something like ahead is this visual representation of a toilet, go hard right towards a visual representation of a door, ahead is a wall, go moderate right towards a visual representation of a corridor, and so on. And then from that, the second stage will generate a fluent natural language instruction in whatever language is indicated by the prompt. So here's the example of the actual output for that input in English, Hindi, and Telugu. So in summary, this is the sort of two-stage approach. We've had a sequence of panoramas along some path as an input. We have a model that detects landmarks and visual landmarks along that route. And then in a second stage, generates this full instruction here to describe how to follow that trajectory. I can stop if any questions are coming up, or otherwise we'll have a look at the results and the evaluation of this.
Let's see if we have any questions from the audience. Okay, so I have a couple of questions. So how much data have you collected? Maybe you've mentioned it, but.
Yeah, the underlying navigation instruction data set is 127,000 instructions. So this is an existing data set. Out of that, we've extracted about 1.1 million of these landmark phrases and grounded them into the environments. So this is all, we call it silver data, I guess, because we've used different types of weak supervision to extract that data set, but like there's no extra human annotation here. It's just using what was already existing.
Because the reason why I'm asking is when you were mentioning the landmark data set, you mentioned that it's not perfect. Sometimes it's not exactly pointing towards the object that we want. And this might be a bit of stretch. I'm just brainstorming here, but I was thinking, especially because this is like people looking at a screen, then tracking their gazes is not super expensive. And it can be relatively easy, especially even like with just one camera on the computer. And I was wondering if you think that will kind of like ground this landmark data set, or give us some idea of how accurate all these is, or even like use this data to improve this data set even further. Is this something you've explored at all? And I know this is a bit of stretch because it involves like adding more noise of the sensors and all that, but it might be worth exploring.
Actually, I think that's a really neat idea. So the evolution of the sort of data collection methods for this instruction following stuff, in the first examples, nobody collected anything from the annotators at all, apart from what they wrote for the instruction. And so in the RxR data set, we sort of thought, hey, maybe collecting a record of where their virtual camera is pointing is going to turn out to be useful. And I think what you're suggesting is the next step that would be even better, which is to add some actual gaze tracking on top of that, because ours is just, where do they point their virtual camera? And I think the reason that would be useful is because, yeah, like, people will recognize an object in their viewfinder without having to point exactly at it and see it right in the middle of the screen. And so if we had the gaze tracking that you mentioned, the next time someone collects a data set like this, I think, yeah, that would be a fantastic idea. Yeah, cool.
Hi, I had a question about the instruction generation part. So if you don't mind, could you go back maybe a couple of slides to that one?
This one?
Yeah, one more back. Yeah. I don't fully get what exactly is happening here, I guess. So once you have the sort of landmark annotations, is this the input to the model, like the thing on the right hand side?
Yeah, let me try to make this more clear. So the thing on the right hand side is the input to the model, and the visual features here are the landmarks that were identified by the first stage, the landmark detector. I probably wasn't sufficiently clear about where the text part here actually comes from. So we assume that we know the position in space of the panoramas that are in the path. So I guess if we go back to what the sort of, this is probably too far. Okay, this will do. If we go back to this, we assume that we've got these panoramas along these cyan, locations, and we know the 3D position of those, so that we know that when you move from one to the other, whether you have to change direction and veer left, or whether you keep going straight, and those types of things, we know. And that's what we use to construct this these textual parts here, using a really simple rule system. So we assume that the person or the agent following the path is basically facing forwards from one panorama to the next. And so we know the direction of the landmark relative to them. And we have a simple setup where if it's within 30 degrees of in front of them, we'll say it's ahead. Whereas if it's, there's a phrase here, moderate right, if it's within, whatever angle that's slightly to your right, we'll say moderate right. And so we will just programmatically build this template around the landmarks, and this is just based on the geometry of that path. Does that help?
I see. Yeah, that helps. Yeah, I was wondering, where you got the actual directions from.
Cool. Yeah.
So then this the instruction generation model, like I guess it translates and then it sort of annotates each, like it converts each visual representation, or does it sort of mutate the text so that it doesn't quite follow this rigid template? What exactly is the role of the instruction generation module here?
Sure. So the text that's in this template is purely it's purely a template, and it's very simple, and it doesn't sort of cover the range of expressions that a human might use. It's also a little bit long-winded in that sometimes there might even be landmarks and things here that aren't mentioned. And so the aim of, I guess, this second stage is to learn to map this into something that's just much more natural and more easily followed by a person. And of course, part of that means replacing these visual representations with their actual like textual description, like the commode and the washroom and the arch and the sofa and so on. So it's sort of a translation from a text plus visual input to a text output with producing something that's more natural along the way.
All right, yeah, makes sense. Thanks.
So yeah, I guess the next sort of question, of course, is having done all this stuff, bootstrapped a data set, trained this two-stage model, how do we evaluate it? And our preferred method for this was to just use human wayfinding evaluations. So basically, you can see with this video what that looks like. someone will basically be shown an instruction. They're in one of these environments, sort of hopping around in between panoramas and changing the direction of their camera, and trying to follow that instruction. And to evaluate whether the instruction is any good or not, we basically evaluate the quality of the path that the person generated in terms of how it compares to the actual underlying path that we tried to describe. And the metrics used for that are shown on the right-hand side here, but it's at high level things like the navigation error, which is the difference between the ending point and the true ending point, the success rate for when navigation error is less than 3 meters, and then SPL and DTW. These are a little bit more sophisticated approaches, I guess, to comparing an entire trajectory. So in terms of how this plays out, we've got success rate and navigation error here. On the left-hand side, so this is for paths of from the validation set of the R2R data set. So these are paths that are on average about 9 meters long through these indoor environments. And for reference, we also evaluated a couple of these previous works from the speaker follower paper and the environmental dropout paper. So they're in blue. In orange, we show some ablations of our model, and in black is humans trying to follow instructions written by other humans. And so you can see that we actually did manage to bridge a lot of the gap between sort of where the state of the art was and the level of quality of instruction that a person can produce. And there's a couple of different components to that. So the first step here is actually just changing the data set. So the previous models were trained on the R2R data set. We trained on the RXR data set, which is a lot bigger, and that helped. Beyond that, the next two kind of largest contributions to performance, one was using the MT5 model, which is just a very strong transformer setup, along with the mural image features, which are also very strong, courtesy of having trained on 2 billion web images. The third part of the contribution, which is probably the smallest of those, but still 6% success rate, is from the landmark modeling. So that's comparing to an approach where we didn't actually model the landmarks and we didn't use the Bootstrap landmark data set. So on top of this sort of very strong model, using the best data, using the best features and the best transformer setup, landmark modeling still adds about another 6%. And this almost closes the gap to human performance. So in terms of success rate, we got to 71% versus 75% for human. And for navigation error, that was almost the same. We also had some results on the paths.
So I think, Peter, we had a question on the previous slide. Bruce, back, go ahead.
Yeah.
I have a question. So, so human evaluation might not be ideal here because the instructions are kind of simple and say like go to X or turn right and these types of things. So I was wondering if you have any evaluation on like VLN or R2R type of data sets. So the language is a bit more complex compared to what you've generated. So have you tried like training on this data set, on this generated data set, and evaluated on those data sets with more complex language?
I'm not sure if I fully understand the question. So what we trained on was RXR. So we're generating the same, I guess, language domain as RXR. We do have an experiment where we got a trained agent that was trained on RXR to follow these instructions. Is that along the lines of what you were thinking, or?
My question is like, what is the evaluation set? Is it RXR or is it this this generated data set?
Right. So the evaluation is based on the paths, and so we actually have, I guess, multiple types of evaluation. The one that we were just looking at, it only depends on the path and then seeing if a person can follow that path. So we have that for, this was for R2R paths. This set of results here is for RXR paths, which are longer and more difficult. And in this case, the gap to human opens up a bit more. So there's still some way to go there. We did also you can do like a textual evaluation where you compare the generated instruction to a reference instruction for the same path. We have those results. I honestly don't find them super helpful because with this task, you can choose to talk about different landmarks. And if you do, you might produce a high quality instruction, but the text will be completely different to a reference instruction generated by someone else. So it's not a task with a lot of sort of inter-annotator agreement, and that makes these like textual evaluations difficult. The only, I guess, other evaluation that we have is this one. So primarily what we really want to do here is to go and train VLN agents on this data and see how much it helps. And I would love to show you those results. However, because this is our kind of most recent work and this is the direction we're traveling, and that's what I wanted to talk about, we don't have the full set of results for that yet. So that's
that was my question. I do have results on those data sets. I mean, automatic. Yeah.
So yeah, let me answer that. So the one thing we have done that I can kind of share so far is that we took a state-of-the-art agent, which is this HAMT agent. We didn't retrain it, but we just gave it instructions from our model during inference and compared that to instructions from humans. And in that case, there's really very little difference. And so I guess one data point is that to a state-of-the-art instruction following agent, it cannot tell the difference between the instructions that we generate and the ones that humans have generated. So that's sort of encouraging that now we can produce millions of these, and at least from the agent's perspective, they're just as good as human. The other thing, I guess, to touch on this point is that we're just going to release all the data, and then we're going to try data augmentation experiments, but we'll throw it open so that anyone else in the community that's interested can use this data as well. So in the next couple of weeks, we're going to generate 1 million instructions from this model for RxR style paths as part of the camera ready for the paper. And we'll also release the silver data set of all the landmarks, which is about 1.1 million of these grounded landmarks. So yeah, very excited to kind of see what does this do from the data augmentation point of view. Given my desire to kind of talk to you about the most recent things that we're working on, don't have the full answer to that yet.
Yeah, cool, thanks.
So that basically brings us to the end of the instruction generation stuff. What I'd like to do is, I guess we've got a little bit more time. I can touch on some of the work that we've been doing generating environments as well, and allow some time for questions as we go through. So why generate environments? There's various different simulators and environments that exist for training navigation agents. And there's different trade-offs between AI2 Thor or using Matterport data or using Habitat Matterport, the sort of newest releases, and which simulators you use and sort of all of this. I guess the overarching point, though, is that there is still a scale limitation in most of this work in terms of having a large amount of environments usually means that you're giving up something, whether that's the sort of image quality or you're giving up on the interactivity or something. And so it's valuable to consider how we can automatically generate environments. And there's this sort of ambition, I guess, that what we might like to consider is generating an immersive environment from something static, like an image or a video. Because images of indoor or outdoor environments and videos of these environments are readily available at more or less whatever scale you want. You're sort of back in the internet data regime. So if we could convert images and videos into interactive environments, then we might be able to kind of get huge amounts of diversity to learn navigation. And so that's the aim of this work. Given an input like the one at the top left here, what we want to do is virtually move the camera to some other viewpoints and generate the prediction of what it would look like there, basically. So you can see some examples of that. If you go down to the second row, after we've moved the camera 2.3 meters in the direction of the yellow arrow, this model that I'll introduce is able to kind of generate this new panorama. You can compare it to the ground truth on the right-hand side. And then there's a second step at about 6.3 meters away from the first camera position. And you can see that there's differences between the model-generated prediction and the ground truth. For example, it turns out that the roof of the kitchen here is actually painted with some type of fresco of the sky. And of course, the model didn't predict that. But nevertheless, this is a task that we're sort of starting to be able to tackle. So to give some more examples, here's some outputs from this model where it was basically given a view from a single position as an input, and then we sort of move the trajectory of the camera through space until it sort of breaks down entirely. We can see how far it can move before that happens. So this work was actually published at ICCV. The approach to this is something like this. It's based on point clouds, and we basically relied on getting RGB depth and semantic segmentations as an input, and we would convert this image then to a point cloud, move sort of through the point cloud as you can see here, and then use a GAN to kind of re-render the point cloud and improve it at the new position. So that's the sort of overall approach. The actual model that we published for this at ICCV was pretty complicated. It had a whole first stage that just dealt with the depth image and the semantic segmentation, and then a whole kind of second stage that just dealt with the RGB, and these were trained separately and had their own, I guess, idiosyncrasies. One thing we've worked out in our most recent work here is that we've been able to do this in a really simple way, it turns out, which is basically just using a single GAN with an encoder and two decoding outputs, one for RGB and one for depth. And so on the left-hand side, we take some image and depth as input. We reproject that based on a point cloud to a new position, and then we simply use a GAN from there to fill in the rest of the image, to in-paint or out-paint as necessary. So this particular image here is kind of busy, but if you look probably at the bottom row, you can see some of the comparisons between our model and the previous work. There's also some comparisons here with recent work on this a model called SynSyn that was also published at ICCV. Sorry, I meant to say PixelSynth that was also published at ICCV. So if you look at the sort of two columns towards the right-hand side, you can see the generated predictions. And where PixelSynth often just sort of creates a blank wall to in-paint the image, our model is a little bit better at sort of generating what looks more like the next room, for example. Conscious that I'm running out of time a little bit, so we did human evaluations on this. The fairly simple model GAN-based approach we proposed turns out to be preferred in human evaluations compared to the previous work. But what I wanted to specifically make sure I could mention was we did our first little foray into training navigation agents using this generator as part of the training process. And so what we did was something that you might call trajectory perturbation. We basically, in the training set, we have these camera captures of panoramas through the environment. And what we used this model for was to move those cameras around after they've been collected. So to sort of spatially perturb the camera locations post hoc. And doing this, we can create new trajectories through the environments that didn't exist. And none of this requires a simulator. This is just based on taking a camera capture, or, this could be a capture directly from a robot. And then after the event, you can generate perturbed version of those trajectories by moving the camera virtually. And so what we're aiming to do with this is just reduce the overfitting to the sort of incidental details of the training trajectories. That's a bit of a problem with tasks like this. And we also compared to a couple of other options. So one is using SimClear, which is basically a range of different image space augmentations like cropping and changing color and so on. And then we also compared to incorporating renders from the habitat simulator into training at the perturbed positions as well. So in this sort of floor plan view, the green is the original trajectory and the blue dot is, where we've like moved the camera after the event. In terms of how this plays out, so on top of a very, very strong baseline model that used the mural features that we've used in most of this work, the trajectory perturbation does improve the success rate by about 1% or about 1.5% when you throw in the renders from habitat as well. Although, of course, the trajectory perturbation doesn't require a simulator or any of the 3D reconstruction. And adding this on top of an existing model gives you something that's state of the art on the leaderboard for this particular data set. So this was kind of nice. This isn't the end of the story. This is really just a first step towards probably what's a larger ambition to train agents in environments that we would be able to create from static images and videos. So yeah, thank you so much for having me to this series. Generally, what we've been focused on here is generating synthetic instructions and a little bit also generating synthetic environments. And if there's more questions, I'd love to discuss.
Thank you so much, Peter. This was a very interesting talk. We have some questions. Kunal, go ahead.
Hey, hi, Peter. Thanks for the great talk. So first, I just had a clarifying question. Were these models that you talked about with trajectory perturbation and everything, were they trained with imitation learning or were they like reinforcement learning models?
It's actually trained with a combination of imitation learning and A2C. So there's some RL. So yeah, this is kind of, I guess, interesting because if you're doing imitation learning, you generally need to do some additional trajectories to show error corrections that might not exist in your perfect human demonstrations. So this is definitely something that's of use for imitation learning, but in this case, it was also an RL approach.
Okay, got it. And the second question I had was that you showed a pipeline for generating environments from static images and videos, and like that was pretty complex. And I guess the complexity is because you need these environments to actually be like really realistic and like they look actually like the ground truth. But I was wondering if, given that the application is navigation strictly, is it okay if our generative model doesn't model all precise details of the environment in a very fine-grained way? What if we use a lighter model that does a better job and like it's possible to deploy that on the fly, and even if it doesn't generate very fine-grained details, and it could be still useful enough for like navigation models, right?
Yeah, I think that's a good point. So one thing we were a little bit constrained by is that the agents that we've been using in this particular setting have this 360-degree camera. And so the image resolution that the agents are consuming is actually pretty high. More realistic for a lot of other settings, you have some forward-facing perspective camera with much lower resolution. And yeah, in some ways, we kind of made it hard for ourselves because of the particular agent we were using. I think you have a good point.
Yeah, got it. Thanks.
Do we have any more questions from the participants? I have one more question. So as you were talking about basically the path dreamer, or I think you called it path dreamer, my brain was just yelling Nerf, 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 with all the success that they have had. So I was wondering if you tried that with like multiple frames that you're having to have a more fine-grained or kind of like refine the images that you have made, because it might, like using the Nerf models, it might actually help you to produce better results. Have you looked into that or not?
Yeah, so the Nerf developments are really interesting. We're sort of watching that closely, and it may be the case that, I mean, that's moving so fast that it may sort of take over. At the moment, though, for this particular setting, we're basically dealing with a situation where at inference time, you get one image or a couple of images, and then you have to extrapolate beyond those. And that's not exactly what the Nerf models are sort of well set up for at the moment. So they're mostly better at least in the initial setup was have a lot of images, effectively optimize on those images, and then generate, novel viewpoints, right? Here, I guess we don't need to just generate a novel viewpoint. We need to infill a whole bunch of stuff that we never saw. So the agent goes and looks around a corner, and we have to somehow hallucinate or imagine what's in that room, and we have sort of very little input to begin with. And at the moment, the Nerf models aren't really, I mean, this seems to change day by day, but yeah, like at the moment, like when we've looked at it, that hasn't really been something that Nerf models can do. But I mean, who's to know what happens in the next 6 months to a year?
Yeah, I think one thing I was thinking is giving the Nerf model basically the hallucinated images that you've had and see if it can refine those views. So basically giving those multiple frames that your model has hallucinated, and then trying to generate an image from a viewpoint that you might already have seen, but you want to kind of refine that in a better way. Because I have worked with GANs and I know how hard they are to train, and sometimes they have some artifacts. So I was wondering if those can help refine those outputs. But I agree, like Nerfs are every day something new comes out that might actually take over all these methods.
There's another sort of direction as well, I guess, in models like mask-git and transformer-based models for image generation and image inpainting, which are also getting extremely strong and more straightforward to train than GANs, it seems. So yeah, there's sort of, I feel like there's a number of directions converging in this space, and things are moving very quickly.
Thank you so much. Do we have any more questions?
I have one quick question, if you have time. So I was just curious about the path treatment model. Like, so it was pitched as like a world model for into navigation situation, right? So I was wondering if you have a model for like generating instructions based on like it can generate high quality instructions, and then you have a path treatment model which can hallucinate trajectories. So have you ever thought about like throwing away the simulator in the first place, and it's like your path treatment model can just hallucinate trajectories, and your instructor generator can just label those trajectories, and then you train a model on that. So you basically have a model that's like free from simulation data, and you can directly try it out on the evaluation set. Like, is that a possibility you guys are considering, or is there like some bottleneck that I may have missed out?
Yeah, I think what you described is sort of the dream that we'd love to sort of get to with sufficient quality, that you can take some very minimal input, like just an image or a real estate walkthrough on YouTube, and that becomes your training environment, and then you throw a whole bunch of generated instructions on top of that. You scale this up, and you can hopefully sort of just ultimately crush this problem. But the other thing that you mentioned about using it at inference time is also really interesting, in that if these path dreamer style models get good enough, they can basically give you an accessible way of sort of planning for things that are around the corner that you haven't seen yet, and potentially using that as a prior, so that if you're doing object nav or something, you're searching for some object, you can sort of do rollouts in one of these models to figure out the likely locations where that might be. So yeah, that's also something that feels to me like is a use case for these models.
Yeah, like one thing that I find interesting about the fact that this model is generative, that if you have some latent vector which the decoder is transforming into a full-blown image, what one might consider doing is that if I'm starting in a room, I can throw noisy vectors to my decoder, and it will hallucinate various positions, and like using that I can just generate free training data. Like throw a noisy vector into my decoder, I generate a new viewpoint, and I just have to get to that viewpoint. So basically the agent can mentally practice navigating to different things. Like these kind of things have been done for like interaction in robotics and everything, but because they consider like very small environments, so they don't really have to deal with actually generating realistic images.
Exactly. So all of this sort of, training in a dream and stuff has all been done in Atari and in simple environments and even in Doom. And I think the exciting thing is we're sort of getting to a point with image generation that we can apply these methods to sort of real world situations, real world environments.
Yeah, there's a philosophical question here. Like, so for example, is it better to generate like everything in the scene? I mean, it's or is it better to generate like task specific stuff? For example, when my agent walks, my agent goes around the room, like the task is navigation. For example, why should I care about like the texture of the carpet? So that's not really important. Or why should I care about like what's on the ceiling? So I can easily ignore that and get better reconstruction for that specific task. So what are your thoughts? Like, should we go for like full reconstruction, or should we make these task specific?
Yeah, so I think it might matter for sim to real in some situations. So, for example, with things like point goal navigation, there's been work from Georgia Tech and Facebook and other places, and well, I guess you guys are doing it as well, but not from the Matterport environment so much, but from like the Matterport setting. How do you solve this sim to real gap from training on the 3D reconstructions and then going and putting this on a robot? And in the sort of point goal task, it doesn't make such a huge difference, and that problem seems solvable. I think where that gets more interesting is with language-based tasks, where you've got language that's referring to all this stuff in the environment. And in that case, I still wonder whether the sim to real gap is going to be higher or harder, because in order for the language groundings to sort of all work, you're not just treating the world as an obstacle, you're actually treating the world as entities that you have to ground to. And so, yeah, it makes me think that in language situations, the realism of the environment will matter more. But yeah, I guess it's still hard to say. And as you say, like, it might be selective. There might only be certain objects that matter depending on your instruction.
Okay, thank you so much, Peter, for the really great talk. And I think these were all the questions we have all been thinking about as well, and are very important in the domain of embodied AI. And I think I'm saying this on behalf of everyone, that we are looking forward to see the follow-up works, and keep us posted. And thank you so much for coming today. We really enjoyed hearing your talk, and I hope we see you in in-person conferences, hopefully in very close future.
Yeah, me too. Thank you so much for having me, and thank you for the lively discussion. I appreciate that.
Thank you.
Thank you so much. Yeah, see you soon. Bye.